here's my completed file, and I have the breakpoints and the rates set differently than the two examples on the sheets. And the important thing about the sheet is that I'm not asking you to create those two graphs that I showed you on the sheet. Rather, I'm asking you to create this file that when you enter the breakpoints, so right now the breakpoints are 1, 5, 5.8, and 8.3, and the rates, that it will graph the piecewise function according to the breakpoints and rates. And there's just one command line below this, right? So there's one math line underneath this that does that. Okay, so if I come in here, and so right now if I change, let's say I change breakpoint 1 to 2.5, and then let's make rate 4 not so steep, so maybe -1/4 instead of -4. So every time I update the file, or every time I update the rates of the breakpoints, it will graph accordingly. So let's get this thing out this way. So I want to move breakpoint 2, say, or breakpoint 3 way out to 10, and breakpoint 4, 16, and then rate 3, let's make it, instead of 6, let's make it 1/2. Okay, so this is the idea. So a couple things, let's see. So some of you are asking, do the breakpoints have to be negative? No, the breakpoints can all be positive and in this order. So 0 is less than breakpoint 1, is less than breakpoint 2, is less than breakpoint 3, is less than breakpoint 4. Okay, so there is, make the breakpoints all positive and each one greater than the previous. Okay, and then but then the rates can be anything, positive or negative. When you make your file, it should what you type in, what you have, should not keep getting bigger and bigger and bigger. If it is, you're missing it. You're missing kind of a big, very, very important kind of thing that we've taught about this class with constant rate of change, right? So what do we got? We got constant rate between the breakpoints, and we're representing every correspondence point between that breakpoint and that breakpoint with a constant rate. Okay, so the very, very important theme and construct that we're working on the last couple of weeks is what you want to apply here so that your file doesn't get away from you, right? So you get a short line, then a longer line, then a longer line, then a longer line, then a longer line. So that's not efficient, and you might be able to get it to work, but it's certainly not efficient and hard for someone else to read. And so we want to make things as concise and short as we can and use the things we've learned in class. So, any questions about that? And then yours won't, I just put these grids in. Yours won't have these grid marks, but you could put these in using remember I showed you that thing about the repeated elements, right? So it would be easy to create your own graph paper like this. And then I think I'm just using the color gray. But in one command line, you can make all the horizontal lines, and in one command line, you can make all the vertical lines, like I showed you in class last time. Okay, any questions? Okay, what about the project proposal? Any questions on that? Okay, very good. So then I'm gonna, later in class, at the right kind of, and this has the right segue in the lecture, I'm gonna show you the next GC file, which is a little more, it's more like the project where you did the smartphone changes. It's a little more like on that level of length and difficulty. Okay. Once you figure out the generalized piecewise, how to do it, that just goes fast. That should be pretty easy. So let's keep going with where we were at, and I think it was in this We were doing this, right? So we were talking about the oil rig, the function RV. So just make sure, are you ready to go on? No comments, questions about homework or the assessment or anything? Okay, so so the function R sub v gives the rate of change of volume of oil expelled per day in a rig that begins to leak at t equals 0 days. And so we're just, last time we introduced this problem of, you know how fast, let's see, where am I? Why is it not doing anything? Oh, these are coming up. Okay, so yes, we did this. So what did we do? We were taking the rate function, and I said, let's break it up into intervals of 0.4 days. Really big moments, right? Really big, unrealistic moments. And so then we found we symbolized or expressed the exact values of the rates at the endpoints of those intervals with function notation, right? And we also estimated those values looking at just picking it off the y-axis, just gave a loose estimate. And then we said, we're going to take this nice exact changing rate function and we're going to make a constant rate in each interval according to the rate at the beginning of each interval, right? So there's the rate at the beginning of the interval. Let that be the constant rate for the whole interval. Next interval, you got the rate at the beginning. Let that be the constant rate for the whole interval, etc. Okay? And so if R sub v is the exact rate of change of volume, v, then just R is this approximate rate function, or like pretend rate function. It's pretending to be the exact real rate function. Okay, so this is a new function created from the exact rate that approximates the actual rate. So what comes first in this process? Actual exact rate or approximate rate? What comes first?
The exact.
Okay. Angel wants exact. What about the rest of you? You agree?
The exact as well.
He thinks exact. Does everyone agree with that? Okay, so this is like over the semesters, I've asked this question actually on a test. So I'll ask this question like, there's this progression of functions. Which is first? Which is second? Which is third? And lots of students say that the approximate rate function is first. Why do you suppose that is? And it's not for lack of being explicit about we're starting with, in class and in homework, we're starting with an exact rate function. We're going to, choose intervals and then build these constant rates to build a new function that's pretending to be the exact. So it's not a delivery or a teaching error. What is it about that you think that students, get to the test and they say, oh, the approximate rate function comes first? Any ideas? And I'm serious. I'm sincerely asked. I don't have really an answer in mind. I'm sincerely asking that question.
I think it might be because that's the first step I guess we take, what we're doing, but
Okay.
Thinking about it, we're using the exact rate of change function, so that really comes first.
Okay, right. So it's the first thing that you do. Okay. Any other ideas? Yeah, I mean, the only other thing I can think of is it's this question that I ask: if we have the exact rate function, so the idea is maybe that the exact rate function would be the goal, and it would come from an approximate rate function. I mean, maybe that's what students are thinking. So I asked this question again. It's a super important question. I asked it on Thursday. If we have the exact rate function, why do we make this very bad approximate rate function? Why do we make this very bad pretend rate function if we've got the exact perfect rate function? Super important question. Why are we doing that? Let's see, Sarah, Donna, Elizabeth, Ashley, any idea? Why are we doing that? We've got the exact rate function. It's perfect. It tells us the rate of change at every moment. Why do we do this? Why do we make this very bad approximation of it? What's the point?
Is it because it takes too long to find the exact at every single moment?
Okay.
Because there's too many moments.
Okay. All right, that's true. We found that out last time, that we focused in on one moment and we created the exact accumulation function right at that moment. And if we did it that way, it would take forever. Okay. Okay, so then we changed gears, but then the question is, why do we do this? So why do we do this? So yeah, and the key is that we're trying to what? We're trying to build exact accumulation. We're trying to get how much we have of oil at every moment. How is that helping us build the accumulation function?
Shoot, I just like had that flashback moment of when you drew the diagram of it said like 3 parts. It was like something rate of change and dy equals mdx, and then it led to accumulation. There was some like connection from rate of change to accumulation.
Yeah, exactly. What's the connection from rate of change to accumulation? What's the connection? What's the connection? Given the rate, given how fast it's changing, what is it that allows us to start developing how much we have?
The constant rate of change.
Okay, constant rate of change. And so how does the constant rate of change get us to accumulation? What does it give us that can allow us to build an accumulation function? Yeah, because that's yeah.
M times dx would give you like the change in y.
Okay, so what does that have to do with accumulation?
So like if you know how much you start with, you can always figure out how much like the change in y and add that to your initial.
Okay, change in y is like a little bit of variation in our quantity, right? So that's a little bit of a variation, and if we keep adding that up, if we accumulate variations in y, then we're like doing a running total of how much we have, right? So, okay, so yeah, we're getting closer. So then why do we break up the intervals and make this horrible rate function with these constant rates? Sarah, do you know?
Wasn't it to like consider like the constant rate over that like small variation
Right.
in time?
And why do we have to do that? We want to get dy's, right?
Mm-hmm.
Ashley, any idea?
If we want to find dy, I guess we have to have an m, so doing it that way allows us to get a constant rate, at least for that point.
Yeah. And then with a constant rate, we can?
Yeah.
Get dy's, right? So this equation, dy equals mdx, is for constant rate of change. If we're going to use this equation to build accumulation, we need to have a constant rate. We can't do it with the exact rate function unless we do what we did before, which is just look at a super small moment and assume it's constant just for a super small moment. That's going to take too long. So the reason that we're going to butcher this thing and make it a bunch of constant rates pieced together is so we can use this equation. And get little changes. So this is our key to get going on accumulation, is little variations in our quantity. How do we find them? Using the constant rate, right? Using the constant rate times a little change in our independent. Okay, so I'm going to ask it again on Thursday, and or maybe we'll just put that on the assessment. We'll put this question on the assessment. If we have the exact perfect rate function, why do we chunk it up into these big intervals with constant rates on the big intervals, which makes a very crude, bad approximate rate function? Why is that? Because if we're going to build accumulation, the way that we can build accumulation is with dy equals mdx, which requires a constant rate of change. Okay, so hopefully this is starting to sink in. All right, so let's look at the R function there. And so I want you to, approximately, R is the blue, is our approximate rate function. So what is R of 0.5? So there's 0.5. What is R of 0.5? And what is, and what is R of 0.9? Let's just do those first two, that's fine. And then 1.12. Let's do R of 9, R of 0.9, and R of 1.1. And now I'm asking about R, not RV, R. So what do we think? Let's just do these last two, R of 0.9 and R of 1. So we want to express it exactly and as an approximation. So what do we think? Who wants to try that? Elizabeth, can you do either one of those?
I can try. I'm not really sure. So like R is how much oil is being expelled if it's not RV, or is that like the rate of the blue one?
R is the new function. It's this blue one.
Oh, okay.
It's the new function created from RV that pretends to be the function RV, but with constant rates that are chosen by the actual rate at the left side of every interval. So in an interval, we look at the rate on the left side of the interval, and we let that be the constant rate for the whole interval. And when we do that for every interval, all those steps form the function R. And so I'm then asking, what is R of 0.9?
So then like the approximate would be like the RV of 0.8, right? Like,
okay, so she wants RV of 0.8, which is R 0.9. So that's an exact value for this approximate rate. Do you agree with that? The rest of you agree with that? Okay, what about R of 1.1? Donna, what's an exact expression for the approximate rate R of 1.1?
I think it's the same as R 0.9.
So R sub V of 0.8 again?
RV of, yeah.
She's proposing this. What do the rest of you think? Elizabeth likes it. Sarah likes it. Angel, Richard, what do you guys think? Agree?
Yeah, I agree.
Yeah, for every x value in this interval, for every x value in this interval, the value of R is going to be RV of 0.8 because we took that rate at the beginning of the interval and let it be the constant rate for the whole interval. Okay, does it make sense? So then R of 0.2 is one more example.
It's going to be RV of 0.
He wants RV of 0. Okay, and so that's important that you conceive that, right? So then for every x value in the first interval, the approximate rate is going to be RV of 0 for every one of these x values. So that's how we can build this we can write a formula for this rate function by understanding what we just talked about. So let's do that. So here we go. So we're going to do it. So we're going to write out what this rate function is, and what's that going to require? What's that going to require to express this, the approximate rate function R? Here's a hint.
Piecewise function.
Right, piecewise function. So what's our first interval?
0 to 0.4.
Am I using x's or t's? I'm using x. Okay, so x to 0.4. Okay, and what is it in that first interval? So what is R of x?
RV of 0.
RV of 0 or RV of x? So is it RV of 0 or RV of x?
0.
Right, because we want to take that one rate at the beginning, let it be the constant rate for the whole time. Okay, next interval. Go ahead.
I had a
Please.
Wouldn't it include 0.4 for the first one for the interval?
So let's see here. Yeah, so I'm doing, let's see. No. So you mean not include?
Yeah.
Okay. Yeah, let's see. There's something that's going to happen here where we're going to need to, it's going to be opposite what we think, but we'll just go with that for now because that's the way the graph shows it, right? So it shows it equal to at the beginning and not equal at the end. Okay, so this one will be from 4 to 0.8, and what will the rate be?
R sub p of 0.4.
Everyone agree with that? All right, so the rest is the same, right? So it's just going to be coming like this. Next third interval is from 0.8 to 1.2, and that's going to be R sub v of. What is it? R sub v of what?
0.8.
Yeah, so we're going to pick off the actual rate at the beginning of every interval. And what's the last one? 1.6. So we got two more. So R sub v of the rate at the beginning of each interval. Okay, so this is the blue function. This is now a definition for that approximate rate function. Picking off the rate at the left side and letting it be the rate for the whole interval, all values of x. Make sense? Okay, so now from that we're going to build an approximate accumulation function. The accumulation, the net accumulation of oil in the spilled into the water. Based on R. So how are we going to do that? So here's where we got to apply what we've learned. So let's just say, so this function a over here, where is it going to start? So at time equals, we're starting at time equals 0, x equals 0. What's the value of a going to be at 0? Net accumulation of oil expelled into the ocean.
Wouldn't it be
0?
Would it be 0?
Yes.
Okay, and so then I've got this range here. I want to let's do it first for 0 less than x. Okay, so now here's where I'm going to do. I'm going to put now the less than or equal to's on the right side now. Okay, and we'll see. You'll see why in a second. Okay, so what's the accumulation of oil then at this? So at this rate. So at this rate in the first interval. So now I got to write a rule that gets me actually how much oil accumulates moment by moment. What is it? So this is where the rubber meets the road here. Can we do it? What will it look like? First of all, just like what will it look like? What will this graph, the approximate accumulation, look like from 0 to 0.4?
It should be a line.
He wants a line. What do you guys think? Line because we got constant rate of change. So we're going to have some line like this. Okay, so we got to write the equation of that line of all correspondence points. Have we done that before? Yes, right, do you remember?
We're going to use the idea of m times dx.
Okay, good. So what is m?
M would be RV of 0.
Yeah, so it would be RV of 0, but then in that interval, isn't RV of 0 R of x? Right? If x is staying between 0 and 0.4, then didn't we say that R of x is RV of 0? So we want to use the approximate rate function here. So you're right, it is. It's RV of 0. But we defined this so we could use it, okay? So I'm going to use the rate. Right? So what happens? For any value x, it'll plug into this, and the x is between 0 and 0.4, and it'll spit out RV of 0. See that? Okay.
Okay, yeah.
Keep going.
Yeah.
You can go ahead, Sarah.
So you said that like our R of x that we created would like work for that RV of 0 with the interval that we have, but in this case, it for 0.4, wouldn't it give the second RV of 0.4 because we have in our R of x case
Yes,
that
it will, and that will be okay because those will be the same value for
Okay.
a. So that will be fine.
Okay.
That'll be okay. So we got to finish this. What's the accumulation? How do I write so we said it's a line. It's going to be some kind of line like this. So we need to write the equation of that.
Would you multiply R of x times quantity x minus 0?
Why would you do that?
Because that's dx.
Oh, okay. So if my x is right here, what's she saying? What is dx? Right? So for any arbitrary x in that interval, say right before 0.3 there, let's say 0.28, what is dx?
It's 0.28.
Yeah, but how do we express it? It's for any x. So what you said?
X minus 0.
X minus 0. Okay? So it's x minus 0. And then that's our change in x. And then what do we want from there?
You want the initial value?
Nope, not yet. We don't go from change in x right to the initial value. What do we do? Remember doing this? We worked on it a couple days and then had an assessment on it. Remember? Start with a change in x, dx, and then?
And the change in y with respect to the change in
Right,
x.
Richard, how do you do that? That's right.
There's because we have constant rate of change, the ratio between those changes is R of x times x minus 0.
Right, so yeah, we use the constant rate, m dx, right? M dx. And now, Angel, we're ready for the next step, which is what?
You add the initial value.
Right, which is?
A is 0.
But that would be an infinite loop.
Oh, it would just be 0.
So this time we have to write 0. So look, we started with 0 and we added the accumulated amount of oil in the first x days, which is dx times the rate, right? Dx times the rate gives us dy, or the accumulated amount of oil in the first. And so let's just try to estimate what that is. So the rate was, this is 28. So by the time we get to 0.4, what will we have? What will the accumulated oil be at 0.4? 108? 10.8? Is that right? Check my math. Right? So the rate is 28 times the total change in x in the whole first interval. Oh, I'm in the wrong place. 0.4 is 10.8. Is it 10.8? Or 10 point, What is it?
11.2.
11.2. 11.2. Okay, which is about where I put the thing anyway. So what's going to look like? What's all a correspondence points going to look like between there and there?
A line.
Yeah, constant rate of change. And we just represented all those points with this equation right here. For any given x, the change in x is x minus 0 times the rate, which will, by the rate function, end up being RV of 0, plus the initial amount gives us that. Okay, next line. So who thinks they can do the next line? Anyone want to try it? Sarah, what do you think? You think you can do it?
Yeah, I got the first part where it was r of x times x minus 0.4.
So now we're in the second interval, so our change in x is going to be
0.4 to 0.8.
No, but the dx, this dx that you said. So dx in the second interval, starting at 0.4, will be x minus 0.4, right? Dx final minus initial, okay?
Mm-hmm.
So that's dx times the rate in this interval will give us the change in y, and then what?
Then we add our initial value.
Mm-hmm.
Is it the value from the last interval? So 11.2?
Yeah, but don't write 11.2. We can
A of 0.4?
Mm-hmm. Does it make sense, everybody? So now this is why we did it equal to on the right. So then I can pick off, we can use just a of 0.4, not knowing what that looks like. Not knowing what that value is, we can just let the function do it, right? And so this is from what? 0.4, strictly less than x, strictly less than or equal to 0.8. Okay, and what rate is that? So let's, to get a good sketch here, that's at the rate of 17. What's 17 times 0.4? So when x is 0.8, change in x will be 0.4 times 17 is that 6.8? Check my math.
Yeah.
6.8 plus the original 11.2 is what?
18.
18 exactly? So
Yeah.
by the time we get to 0.8, we're at 18. Right? Okay. Donna, can you do the next line?
A of 0.8 plus r of x times x minus 0.8.
Mm-hmm. And?
0.8 is strictly less than x, which is less than or equal to 1.2.
Right. And why is it x minus 0.8? What is that about? Why x minus 0.8? What is that?
Because it's just the change in x for the interval from 0.8 to 1.2.
Right, and it's arbitrary, right? Like it's every change in x. So x could be any x in there, and then x minus 0.8 gives us the corresponding dx. Does everybody see that? That's what we're doing. So x is every x value in there, minus 0.8 will give us dx in the current interval, right? The amount of change in the current interval. Okay, so we get the point. 1.2. So now it's kind of easy without thinking about it. But setting up these first two is really important that you can recall that and do that without having the this model right above just to write everything down now. So it's kind of too easy. But we like that once in a while. All right, does this make sense? And so what's going to happen? These lines are going to get they're going to have slower, less and less of a rate as we go. So I'm just going to eyeball it now. I just want it to be like a little bit less, a little bit less, a little bit less, something like that. Not accurate. I just kind of threw it up there just to get something. Okay. And so here we see this. So now what do? We built an accumulation of oil. This is the oil accumulating. It so say at 1.7, A of 1.7 is the y coordinate of that. What's the meaning of that point that we get from this function? So what's going to happen? X is 1.7. It's going to come to this line. Can put 1.7 in here and crank this out, but it has to use 1.6 from the previous line. And actually, it's going to have to get 1.6. It's going to have to use 1.2 from the previous line. So it's going to actually work through the whole thing, and it's going to give us a number for A of 1.7. Okay, and then that's that point on the graph, 1.7, A of 1.7. What's the meaning of that point? So what's the meaning of that point in this context about the oil?
When one phase has elapsed, the amount of oil that has been expelled is A of 1.7.
Okay, yeah, good. Since when? The amount of oil that's been expelled since when?
Since the oil started leaking.
So since 0?
Yeah.
Yes. Right? It always includes all the amount from before, right? This function always, it's a running total. It's accumulating, keeping track of what we've had before. So all these values are the net change of volume since 0, right? These are all net change or the amount expelled since 0. Okay, so this is another kind of approach to this. And now we actually have something for 2 days, right? Instead of 0.005 days, right? That's what we did last time. We figured it out, we got an accumulation function for just a moment, a small moment, a realistic moment. And that was good, but we said it would take too long. Well, now we have something that's for a whole 2 days, but what's wrong with this?
It's just an approximate.
Yeah, what kind of approximate? Good or bad?
Bad.
Yeah, probably pretty bad. Why? Because it's based on this pretty bad rate function. Like by the time you get to 0.4 here, based on this rate, is this accumulation going to be a little bit, let's see, really, really low, a little bit high, or really too high? This approximate amount of A of 0.4. How does that compare to what we'll call V of 0.4?
Would it be too high?
He wants too high. A lot too high or just a little too high?
Way too high.
Why way too high? Who said that?
I did.
Yeah. Why?
Because if you even look on the graph, the approximate rate used for that first interval is way higher than the actual.
Right. It's decent here for like 0.1 days, but then at the end of the interval, it's terrible, right? It's way too high. And so at that higher rate, we're going to get way too much accumulation. It's going to be bigger, much bigger. Okay, so we got an accumulation function for 2 days, but it's not good. Okay, it's not good. All right, so this is a good time to pause and take a look at the next GC project. Let me show you what that's like. Can I erase what I wrote on the screen? And before I do that, let me just talk about where we're going next. Okay, so where we're going next is, it's kind of like we're going to take still a third approach to this, right? First approach, focus in on a moment and get a good, just for a little bitty bit of time, get a good accumulation function. That was not good because it would take too long to do it all. Here we got an accumulation function for the whole 2 days, but it's not very good at all because this rate function is not a good approximation of RV. Okay. So then where we're going next is, what we want is, we want to write this. Okay, so how would we make this better? Okay, so how would AX be a better approximation? You probably all know the answer to that.
There were more of them.
More of what?
More intervals.
More smaller intervals, right? More smaller intervals. The rate, those constant rates will do a better job mimicking, pretending to be the real rate function, right? And then our accumulation function will be more smaller segments, more shorter segments that would get closer to the actual. Okay, so what's the problem with that? So I'm going to use more and more intervals. Then what's going to happen to this form of this A function when I use more and more intervals?
There's more equations in the piecewise function.
What's that?
There's more equations in the piecewise function.
Yeah, so more, right? That's an understatement. If we want to make it really accurate using this approach, how many will there be?
A lot. A very lot.
A lot. And we don't want to write out a function like this. We don't want to write, 100 or 1,000 lines in a piecewise function, right? So then where we're going next is, we want to write this function. It's going to do the same thing that this one does, but in one line. Not broken up, not one line per interval, but one line that'll take care of do the whole function, for all intervals. That's where we're going next. Because we need to make these, to get some accuracy here, we need to make these intervals smaller, and when we do that, we'd have too many piecewise lines. So we need a form of this that can do it in one line. Therefore, no matter how many intervals you have, it'll still be one line. See that? That's where we're going next. All right, let me show you the GC file. So it's based on the oil. This is still the oil situation. I've got this. This is a cool project. All right. So this is this familiar exact rate of change for oil. And so what happens on this one is, you can pick a starting value with the A slider. So right now A is 0.825. So it's showing the start of this little interval here is 0.825. But I can change that. So come over here. Now it's 1.75. So that's right here. See the start of this interval. And then once you have picked an A value, then by the N slider, what happens is, the N slider then accumulates or starts varying in that interval. So look over here at the left graph. So it's going to vary in that interval, and so you're going to see that constant rate emerge like that. And so the width is, I think it's always, is it 0.5? What is it here? Oh, come on. Skipping it. It's there somewhere. I saw it. There it is. There it is. So what do we got? 0.5. So interval width is now 0.5. Okay, and then you can watch the point. If you let n is going to increase from 0 to 1, and as n increases from 0 to 0.5, as n increases from 0 to 0.5, it will track the point on the approximate rate function here. You see that? So one more time. So as n increases from 0 to 0.5, it shows all the points on the approximate rate function at the beginning. It's from the beginning of the interval to the end of the interval. And as it does it, this over here, it's going to show a little bit of the linear accumulation function. So watch that. So it's going to, as you increase n from 0 to 0.5, you'll see this line emerge to 0.5, and then simultaneously your change in oil will grow, and then it will generate all the accumulation, the correspondence points for the accumulation in that interval. But this is based on, right? This is based on this constant rate of change. So notice kind of the inclination of that. If we go back to the beginning, say A is 0.3. At 0.3, for the same change from 0 to 0.5, now look at the change in y and the pink graph. See that now is according to this constant rate, starting at A is 0.3 now. Okay, again, so, and then if I start way back at 0, say, that's the highest rate of all, right? That's the highest rate of all. Let x go from 0 to 0.5, and it shows this thing being created at the highest rate, whatever that rate is. Lowest rate, over here. In the middle there, perfect. So here's the triangle forming at the lowest rate. Okay, so in addition to creating that animation, then you're also going to, your file will have the correct symbols for all the question marks. So what quantity is this right here? You're going to put that there. What quantity is this? As n changes, that quantity changes, right? What is that? Same with over here. Same with this. So you're going to fill in, so your finished file will not have question marks, but it will have the appropriate symbols there. And so I think we talked a little bit about the symbol command. It's just a point, right? So you're going to graph a point, and then you do comma, symbol equals, and then quotations, and then whatever you put in the quotations, that will appear at the location of the point. But we did that before, right? You guys worked on that for the smartphone project. All right, questions on this one? So this is really good because it forces you to do this construct correctly. You got to know the math, right? So you're going to be having to apply the math that we're talking about in order to get this to work, right? Because you're doing that. You're graphing all correspondence points on that accumulation. So as n increases, it's sweeping out all the correspondence points of the approximate accumulation function in that interval. So and then the starting value I just have it at 3 for all intervals, right? So we're not gonna think about all previously accumulated oil before the interval. You can just have it start always at this y value of 3 or 5 if you want, doesn't matter. But that would be another aspect to this that we're not considering, is truly at what y value should this start, right? But you don't, for this project, you don't have to do that. I'm more interested in what's happening locally to get the change in y and to build the accumulation function from 3. Okay. So this is all being recorded. So I'll post the video today. Any questions on this very cool project?
So for that last part, you just said that the triangle so what you're saying is that the triangle that represents the changes isn't going to be shifting up.
That's
according
right.
to like the initial value.
Right. So realistically, realistically, the starting value would get higher and higher because it's based on all the accumulation of oil from before. You don't have to worry about that. You can just always start at, I'm starting mine at 3. So look, if I change the starting value of accumulation, the starting x value here, it's starting at the y starting at 3. Change it again, y starting at 3. Change it again, y starting at 3. Okay, what do we think? Any other questions? So you have until you have a week on this, right? So I know you got three things for Thursday, but if you can try to get started, and then that'll give you a chance to, when we meet again Thursday, you can ask a question or during office hours or something like that. But you're always welcome to send me your file of your current progress and ask me over email, and I'll try to get back to you as soon as I can. Hopefully less than a day. So any questions on this? Okay, so then that's, so I think I opened up that post, right? Is that on Canvas? Can you access this assignment? Has anyone seen it? Anyway, if it's not, I'll put it up today, but it's to make this is on the video. All right, so we're talking about, let's see, start here. So we're going to do a new context. And so what I've got here is a rocket basketball. It's a basketball that's rocket powered, okay? And it's flying up here. And this is the velocity versus time in seconds. So it's this is the velocity of the ball versus time in seconds. And so what kind of quantity is velocity? Let me say, is it an accumulation function or a rate of change function?
Rate of change.
And it's rate of change of what, Angel? Velocity is rate of change of what? Did you say something? Sorry.
Is it speed?
Velocity is the rate of change of speed. What do we think?
Rate of change of the ball's position.
The ball's position.
Oh, yeah.
So, yeah, and what's really the ball's position here? What are we interested in with the ball in terms of position?
The center of the ball.
Like the height, right? So
yeah.
Position can often imply more than one coordinate. All here we're interested in is the height of the ball. So this is the rate of change of height of the ball, and so in this new context, like I said, we're gonna start moving towards, with that approximate accumulation function, doing it in one line. So we're gonna ask some questions about this then. So I need that to go away. There we go. So first we're gonna highlight points on the graph every 0.9 seconds. So I had a handout, but I didn't have time to post it on Canvas. So what would that look like? Oops. That's good. So we want to highlight points on the graph every 0.9 seconds. And so then our moments will have a width of delta t equals 0.9. Okay, so 0, then where's the next one? Where's my next 0.9, right? And then where's my next breakpoint?
1.8.
1.8. Then where's next? Fast. Here we go. Fast participation. Let's make it go fast. Next one is
2.7.
2.7. Then
3.6.
3.6. Then
4.5.
4.5. 5.4. 6.3. So and then yeah, let's keep going. 7.2, 8.1, and 9. Okay, and so is delta t of 0.9 a variable or parameter? Remember that? Is that a variable or parameter?
It's a parameter.
Parameter, because?
We defined it to be 0.9, and it's represented by a letter.
Okay.
Delta t, but yeah.
Okay, and then you still didn't get quite to the heart of why it's a parameter. So yeah, it's represented by a letter. Why? What makes it a parameter?
Is it because it could take on a different value if we assigned it to?
Okay, yeah, it has to do with that. Will it? Will it take on a different value?
No.
Yeah, only if we change the situation, right?
Yeah.
So a parameter is constant in the current situation. Okay. So what about t? Is that variable or parameter? T.
Variable.
That varies, right? That varies through. So we got t varying through intervals of 0.9. The 0.9 stays the same in this context, but t varies through those intervals. Okay, let's keep pressing on here if we can. So we're going to sketch the approximate rate of change function using the rate at the left side. So in the first 0.9 seconds, what will the rate be for the approximate rate function?
The rate of 0.
He wants 0. Is that 0? Yep, because at the left side it's 0, so we're going to have 0 the whole way here. And then, in the next interval from 0.9 to 1.8, how can we express this exactly? We want to express exactly what the constant rate will be in that interval.
Is it r of 0.9?
So we're building the r function. So yes, it's something. It's this function taken at 0.9.
What's the RV?
Yeah, like the RV at 0.9, right? Or v at 0.9. So if v was the little v like this, but no, I like RV. So r. No, it's not RV because what would it be? R sub what? Because this is the quantity that we're accumulating.
S for position.
Okay, but remember we kind of clarified not position, but what?
The height.
Height. So R sub
H
probably. So this rate would be R sub H of what?
0.9.
R sub H of 0.9 would be that one. And then what about in the next interval? What will be the rate there?
R sub H of 1.8.
Good. R sub H of 1.8. Whatever that is. Next interval.
R sub H of 3.6.
Right. Etc. Okay. And so here we go. So that's the approximate rate of change function. And that's actually in the next screen, I think. So here's that. And notice what this animation is showing now. It's showing the approximate accumulation function, like we did on the oil spill, being generated. Is that a smooth curve? Is that a curve?
I'll say no, but the video quality makes it kind of smooth.
Okay, so yeah, so it either is or it isn't. So you say it. You say it is. You say I'm sorry. You say it's not a smooth curve.
It's not.
It's not. What about the rest of you? Agree with that? Yeah, piecewise linear, like we did in the oil example, right? So actually, the first interval is a constant rate of 0, right? So you get 0 accumulation in the approximate. And then now we start to head up, and these are piecewise segments, right? Okay. So yeah, R sub H of t, that's actually t to the 1.3. Okay, so our original exact rate function is actually t to the 1.3. Okay, and then the approximate rate function, which is based on the intervals of 0.9. And then here's the approximate accumulation function, which is the piecewise linear function. All right, so we're not going to write this out. So we already did this for the oil example, but we could do it again. And so, but that's important that you know how to do that. So Maybe we'll just do let's just do the first two intervals really fast. So what will I write for my rate in the first interval? And let's rapid fire here. So just everyone just popcorn. Here we go.
R sub h of 0 from 0 to t to 0.9.
Nice. Somebody else. What will be the next one?
R sub h of 0.9. Sorry.
Good.
From 0 to t to 1.8.
All right, and so then we'll write the first two over here. So now what's going to be my, so from 0 less than or equal to t less than or equal to 0.9, what would be my accumulation function?
Zero plus r of t, 0 point, and then x minus 0.9 times 0 x minus 0.9.
T minus 0.9. What do you think?
Yeah.
Everyone
Isn't
agree?
it t minus 0?
What'd you say?
Isn't it t minus 0, not 0.9?
She wants t minus 0.
Yeah.
Right, because it's the change since 0, right? So we're in the first interval. So we want dt is going to be t minus 0. Do you see that?
Yeah, my bad.
No, but you did great. Okay, and then who wants to do the next one? So from, 0.9 to 1.8.
It'd be a of 0.9 plus r of t times t minus 0.9.
Good. All right, here's the beauty of this. You know every piece of this, what it means, right? It's not just a form that you're plugging into. You know what's happening. Starting at 0.9, we have some change in t. It's that much, right? That's dt. And then we multiply that by the rate to get what? What will this be?
Your dy.
What's my y in this case? What are my y's? Because I don't really have y's here.
Change in height.
Yeah, so this is like dh, right?
Yeah.
So given a change in time, multiply by the constant rate, you get the change in height, and then you do?
At the initial height.
Right.
Do
We're
we have
accumulating height, right? We're keeping track of all the height from before, and then we're adding on height bit by bit, keeping a running total of the height. That's what this function does, but based on the approximate rate function, not the actual rate function. That was good. Go watch the video and listen to what I just said the last 20 seconds. That was really good. All right. Richard, what were you saying?
Do we have an issue with like the inequalities on the rate, approximate rate function?
What's the issue?
Because if it should, I believe like the right hand side should be strictly, and the left hand side should,
Okay.
of the domain.
What about it? So he wants these to be strictly less than, and then these.
The approximate rate function to the left.
Yeah, you want these to be strictly less, and these to be less than or equal to.
For R of t, yes.
For R of t.
Yes.
So.
Because if you put 0.9 for like the second line of the A of 2, if you put 0.9, your rate of change, your constant rate is R of h of 0. Instead of R of h of 0.9.
But so that's fine, right? That doesn't cause an issue, right?
Are they not different values?
Well, so this is just doing it the other way now. So it's doing it like this.
Oh.
That's how now. So and actually, it kind of needs to be like that if we're going to do the accumulation function that way.
Oh. Okay.
And you know why I'm doing the accumulation function that way, right?
Yes.
Yeah.
Yes.
And then to be consistent, we'll just do the rate function that way also. So it's a little, when you're first doing the rate, approximate rate function, it's a little counterintuitive, but then you see why you do it when you get to the accumulation function. So it's like open circle on the left and closed circle on the right. Is it okay?
Works okay.
All right, cool. All right, so now let's start talking about, we got a little time left. We're going to start talking about then this other way, right? So we're still on this, a line for a math line for every interval. We don't want that because we know intervals need to get small to make it accurate, and we don't want a gazillion lines. So we're going to start working on the one-line version here. So here we go. Here's what we're going to do that. That's what we already did. See that nice, pretty version in the video? Okay. All right. So now, I want to do something a little different. I want to find the approximate height of the rocket at t equals 5. But I want to do it with a direct calculation. I don't want to use this a function that keeps, looping back to the previous line, right? Plug in 5, and then you need the starting a of that interval, and you need to go back to the previous line, and you're right. So I just want to do a direct calculation with all these principles that we've learned, right? So we're going to use the same principles we've learned. I would do a direct calculation of a of 5. Okay, and so what is that? A of 5 is right, where's 5? 5, oh, it's right here. Okay, so it's right here. So I want to just write out an expression without a bunch of different function lines that gives me this, right? This right here. Can you do it? Can we do it? Can we write out an expression that would calculate a of 5 just directly without using the a function that we did? What would that entail? What would that entail coming up with the total accumulated height of the basketball at 5 seconds based on our intervals and these constant rates? Where does it come from? Where does this accumulated? Go ahead.
I don't know if we're supposed to be thinking about it this way, but like an interval?
No, much easier than that. We just want to use what we're doing here. We want to use what we're doing here, because the integral won't be helpful because of these big intervals, right? So much more straightforward, much more in line with what we've been talking about. Just applying what we've been talking about. So maybe do you see these little tick marks? Maybe this is a hint. See these little tick marks here? Maybe that will help you figure out, where does a of 5 come from? The accumulated height at 5 seconds based on constant rates. Any ideas? How do we get accumulation from rate of change?
Using constant rate of change?
Yeah. So how do we do it? How do we get accumulation from these are constant rates of change? How do we get accumulation at a constant rate of change?
Is it each interval?
Each interval?
Times the rate within that interval?
When you say
added together?
Okay. When you say each interval, what do you mean? What do you mean? What about each interval?
The change in t.
The change in t?
In each interval.
Okay.
Times the corresponding rate at that interval.
Okay, so do that. So what you're saying, do that for the second interval. What would that be for the second interval?
0.9.
0.9.
Times is it RH of 1?
1? Where did the rate come from in that second interval?
RH of 0.9.
So, and you're saying that will calculate what? What will that calculate?
how much more. It'll calculate how high the rocket is in that interval.
How high the rocket is in that interval. Okay, we're close.
Or how much higher it travels in the interval.
Okay, that's right. So it's a variation in height. It's a variation in height. This is like dH, right? dH equals what? Everybody. dH equals m times
change in h.
G times the change in h?
No, change in time.
dt. dH equals m dt. This is how, given constant rate, how we get little accumulations of height, right? So that's why we did the constant rates. In order to get variations in our quantity that we want, height, using dy equals mdx. In this case, dH equals mdt. So she did that for the second interval. And so that's actually this little amount of height right here, from here to here. Because the first interval gives us how much change in height?
0.
0. So that's just a point here. And so this first little tick mark is showing the first actual variation in height, which is from the second interval. So how could you write out an expression that will give a of 5? Everyone do it. Can you write out a full expression that will calculate a of 5? Quick. Everyone do it. Who thinks they could tell me? So Donna got us started. Ashley, Yasra, Elizabeth. One of you guys? One of you ladies? Elizabeth, you think you got it?
I think I have like the idea of it, but I don't have like the generalized form. So like Donna was saying, we do like the change in like time, which is 0.9 times like the rate at each specific time.
Okay, right.
So then we have to do like 0.9 times like each rate and add them, or is there like an easier way to do it?
Easier way.
Yeah,
we're just being literal here. We're just being literal. Where does this change in height come from if we've got these constant rates over intervals of 0.9?
So it's like 0.9 times like the rate at like 0.9 plus, it's like 0.9 times the rate at 1.8.
Okay. Keep going.
And then plus like the rate at 2.7.
Is this 0.9 or 1.8 here?
0.9.
Yeah.
Because it's 0.9 every interval.
Right. 2.7 times 0.9. Keep going.
And then plus 0.9 times the rate of height at 0.36.
6. Still going.
And then plus 0.9 times the rate of height at 4.5.
Okay.
And then, wait, for that, do we have to make it like less?
Do what you think it is.
Because it's,
yeah, do what you think it is. What is it? You got it.
Well, because in the first one, so 0.9 times rate of height of 4.5, would it be different because it's ending?
Go for it. Yep.
End,
you got it. Follow your instincts.
0.5.
R sub h of?
5.4.
Uh-huh.
And then times negative 0.5.
Negative 0.5?
Or just 0.5.
So how much change in time do we have in that last interval? 2.5.
0.5.
Yeah, 0.5.
Okay.
So look, this is kind of the structure of this one-line accumulation function. So this is just a practice, or just a particular value. But the one-line accumulation function is going to do this. It's going to sum up all the changes, variations, from the completed intervals plus what? A little more change from the current interval. So before she started writing all that out, did others of you write something like that down? Angel, yes? Richard, yes, exactly. So in terms of building this one-line accumulation function, this is going to be the structure of it. This is what we're going to do. We're going to write m dx plus m dx plus m dx for all the completed intervals and add them all up. So that's all these, right? Boom, boom, boom. Add up those. And then there's going to be a little more accumulation in the current interval for the partial interval, and that's going to be, this is this last one right here. See that? That's the, right there is the RH 5.4 times 0.5. So that's going to be the structure, but we've got work to do to make this general for any t value, right? So this was just for 5, right? This was just for t equals 5. So we're going to have to use this structure and build this up so that it works for any t value a of t. And what happens? If at different values of t, you have different number of completed intervals. So this is not an easy task, right? So based on what t is, you're going to keep adding on more and more completed intervals. So, but we have math to do that. We have math to do that. Okay,